So, hello everyone. Let's get ready to dive into our next section on the interstellar medium. And we're going to see lots of gorgeous pictures. Talking about the gas and dust in the cosmos is where we start to see a lot of the prettier pictures that people associate with astronomy. All right. So, the quick outline how today's lecture is going to go is that we're going to start talking about the space between the stars, talking about where is the gas, what is out there, and some of its properties. And then we'll go in a little detail about, we'll distinguish between the dust versus the gas. And the shortcut, we might try and think of dust and gas as the same thing, but as scientists, we'll distinguish them in a bit more detail. And at the very end, we'll start getting our way back into the stars. We've talked about how our sun's this nuclear powerhouse. We, in section 7, mentioned how the protostar forms from the nebulas. Well, here's some pictures of nebula. So we'll go over again how the nebulas collapse down and eventually form the stars. So, for starters, let's just do a quick reading quiz. All right, and we're going to say, all right, astronomers, we're going to use this term interstellar matter, and what exactly are we referring to? Are we talking about just the planets around the stars? Is it a bit more than that? Is it the comets, asteroids, and meteors? Remember when we talked about our solar system, you can talk about, say, like the Kuiper Belt. It's just that region of debris that's around the sun. Is it just the gas and dust between the stars? Or is it a bit more abstract? Is it the radiation, the light, the radio waves that are filling the void between the stars? Or throw away a fortune teller. Obviously, it's not going to be E. So, everyone's on top of this. Yes, when I say matter, we're talking about just the gas and dust between the space of stars, right? We like to shortcut and we like to say space is a empty void, but even in the coldest, darkest regions of space, we're still gonna find stuff. So, all right, let's start talking about what is in that stuff. This is a picture. Great example. We're seeing all sorts of different hotbeds of protostars forming and glowing. The dark clouds here, these bands of darkness, that's what we might call molecular clouds. Just these thick in astronomical sense, thick layer of just debris out there. And it's literally blocking the starlight from behind it. So let's start getting a picture of where we're at, what we're looking at. And here, you might be able to recognize that this is the Milky Way, just the Milky Way galaxy. But instead of being in the visible spectrum, we're watching it in X-rays. So we scan across everything we can see in X-rays, and we just see that we are flooded by X-ray light. And so we realize is that our star, our solar system, is in what we call a local bubble. And in that local bubble, there is a lot of these high temperature particles. Specifically, we'll say that the density is very low. So the number of atoms present, and I'll have some figures to try and clarify that a bit. But basically, the number of atoms present is very low density. But these are very high temperature gases. Remember when we talked about the outer atmospheric layers of the sun? You had the corona layer, which was low density, high temperature gas. Very similar. In terms of density, we can say what the average density is. We'd say there's about 0.01 atoms every cubic centimeter. So take a small little cube centimeter, and there's only a tenth of an atom being in there. Not a huge chance. But those atoms are whipping around very rapidly, right? Remember, temperature is in essence a measure of their average speed. And so, sure, there's not a lot of these things, but they are really, really hot. And that temperature of about 1,000,000 Kelvin is why they're glowing in X-rays. So, some other terms that we can bring into this. We can talk about what we call the interstellar clouds that exist around this local bubble. So this is the local bubble that our sun's about here right now is in. And we've entered a slightly denser region in the last 10,000 years that we creatively called, I'm not even making this up, guys, we call this the local fluff. The density material is just a little bit thicker, whereas around here, it's closer to 0.01 atoms every cubic centimeter. And here, we're dealing with something about 0.3 atoms every cubic centimeter. And the temperature has gone down. This gas is much slower. This fluff is moving at much cooler rates, closer to 7,000 Kelvin. So I keep talking about these cubic centimeters and this density, and I want to use these next few slides to try and give you a little bit of a visual idea of what do we mean. So let's start out density, the number of atoms in a given volume. So let's start. Let's say I have a cubic centimeter of air, a little bit smaller, about a fraction of an egg, basically, right? So take a tiny little bit of air, and in that tiny section, there'll be upwards of 10 to the 19th molecules zipping around and bouncing. So here, take 1 cubic centimeter, and I've got trillions upon trillions of molecules or atoms bouncing around. Well, let's apply a vacuum, right? I'll hook up a vacuum, suck the material out, start trying to pull all the atoms out. And we define a vacuum to be when there's no gas present. Well, even the best vacuums on Earth, they only get down to about 10 to the 10th, about 10 billion molecules per cubic centimeter. So I can still take my little cubic centimeter box, and even though I've put the best, strongest vacuums that humanity's been able to create, we still got about 10 billion particles just flying around, floating there. So now we go into the vacuums of space. All right, we go into that interstellar medium, and there we'll say, look, out in that medium, there's an average density of sometimes around 0.1 atoms every cubic centimeter. Or put that in perspective, here's our cubic centimeter box before. There's 1 atom in a 10 cubic centimeter box. You're getting closer to about the volume of a little egg. So take an egg and go into the deep vacuum of space. That egg will have 1 atom in it. And that's the density that we're trying to deal with. So like I said, space is very big, and it's mostly empty, but a crucial part is that it's not completely empty. Even in the darkest, coldest, loneliest places, you're still going to find some number of atoms just floating around there. And this is where things get complicated. Right? That matter, it's not distributed homogeneously. Think of it this way. It's not like there's just this big pool of water stretched out thin across the cosmos. You're going to have regions where it's very, very densely thick. Nebulas are the perfect example of that. You'll have regions that are even super thick, like us here on Earth. We're a very dense pocket of atoms together. And then you'll have other spaces that are closer to almost no atoms there. So, wonderful question to try and contemplate how much stuff out there is to do a rough estimate of the amount of matter out there. We're going to say how much mass is in, say, our galaxy. And so here's the point. How much gas is there? We know the density is very low for most of space, but we also know space is very large. So let's try and put some numbers to this and figure out basically how much matter, how much gas is out there, and how much of it can be used to do stuff. So we're going to do just a straightforward approximation. And by straightforward, I mean we're going to use the next few slides to grind this out together. But it is a simple setup. I say, how much mass is the gas in our Milky Way galaxy? Well, how big is the Milky Way? Figure out the volume. Say, how many atoms per a volume exists? We've already been talking about saying there's 0.01 or 0.1 atoms per cubic centimeter. So you say, what's the density of atoms in our galaxy? And say, what's the mass of an atom in our galaxy? So we'll start with the hardest one. We're going to do the volume first. So here is our picture. Remember, this is an approximation. Still good if we expect to be within an order of magnitude of the correct value. So in our trick, we're going to take the Milky Way galaxy and we're going to treat it like a perfect cylinder. We're going to say it's a cylinder that is 100,000 light years across and it's got a thickness of about 300 light years. Right? So if we treat this as our cylinder, here's, right, there's our radius, and here's our height of the cylinder. So we can say the volume of the cylinder is just pi r squared, the surface area of this disk, times the height, or the 300 light years. So, go ahead and do that calculation. We're going to have to be toying with units here. So I'm going to go through these a little bit by a little bit. So once again, we're doing this, the volume circle, or cylinder, pi r squared h. Our radius was the length, the radius of the galaxy. So the radius of our galaxy is going to be 50,000 light years. Let's use my highlighter. Right. We're going to have a radius of 50,000 light years. As a reminder, here's our spiral galaxy. There's that radius. All right. Now, the next term here, what's this guy? That's to convert, right? We're in light years. We need to be in centimeters to make all of our units consistent. So all we're doing here is converting 50,000 light years into centimeters. And straightforward, we just say, look, there's 9.5 times 10 to the 17th. There's 9.5, 10 to the 17th centimeters in 1 light year. So let's clear that out a little bit. So we're saying here is our radius squared in centimeters. Now do the same thing for the height of our cylinder. It's 300 light years, and we need to convert it into centimeters again. So same factor, 9.5, 10 to the 17th centimeters, and a 1 light year. Do that calculation, and we're going to find that the volume of the galaxy is this massive number, right? 210 to the 66 cubic centimeters. All right. So we've got the volume. That was the hard one. Now we can figure out the density and the mass of an atom and bring these all together to get the mass of the gas in the galaxy. So table this number off to the side for now. It will come back for us when we actually do the full calculation. And let's get the density. Our density. We've talked about values of like 0.01 per cubic centimeter to much denser regions like 0.3. And so what we're going to do is just make an approximation and say, take a cubic centimeter and put 1 atom in there. And this we're going to approximate across the entire stretch of the galaxy. Say that there's 1 atom every cubic centimeter. Right? And this is basically a balancing act between the regions of very, very low density to regions of thicker densities of like nebulas or even potential stars. Now, we gotta get the mass of an atom. So what we're gonna do there is say how much material is out there. What type of material is most of the universe? And you're gonna see pictures like these nebulas, and a lot of people might jump to conclude that there's a lot of dust grains in the universe. They're gonna say there's a lot of just dust, debris, but it turns out that most of this is going to be hydrogen gas. A whole spectacle of different colors coming from the cosmos, and most of it's still just going to be hydrogen. If we counted up the atoms in the universe, you'd find that hydrogen is about 75% of the universe. So, with that said, we're going to say that just every atom across this galaxy is hydrogen. And hydrogen has a mass. The mass of just the proton is going to be 1.7 10 to the minus 27th kilograms. So we're going to take all of these values, taking the volume, that 1 atom per cubic centimeter, and the mass of an atom to get the mass of the galaxy. Technically just the luminous mass, but we'll touch on that again later in the semester. So let's plug everything in. All right, the volume we found before, 10 to the 66 cubic centimeters. We say, on average, we're estimating there's about 1 atom every cubic centimeter of volume. And that atom weighs 1.7 10 to the 27th kilograms. So stitching all of this together, we're going to find there is about 10 to the 39th kilograms of just stuff out there. So now we're doing this game, like I said, way back at the beginning of, well, this is a really, really big number. What does it mean? So let's rescale this. Instead of talking about 10 to 39th kilograms, let's compare it to something that has a bit more meaning to us. Let's look at the mass of the sun. Remember, circle dot means Sol. So the mass of the sun is about 2 times 10 to the 30th kilograms. And let's just compare. The mass of the galaxy, the total mass of the galaxy, divided by the mass of the sun, right? 3.5, 10 to the 39th, divided by solar mass, 2 times 10 to the 30th. We're going to find that the mass of the galaxy is 1.75, 10 to the 9th times bigger than our sun. So what that means is that in the galaxy, even though it is mostly empty space, there's still enough stuff out there to make about 2 billion more suns. And just our sun, just a average medium sun, there is enough matter in the huge void of our galaxy for 2 billion more of these stars. That is how big space is. That even though it can be mostly an empty void, there is still so much space that there can be room for so much matter. So one last definition to bring in here. We can say the interstellar medium. And this is just a callback from the very beginning of this bit. Right? We're saying all material between the stars. Right? We can find gas, and that gas can be found as single atoms. Sometimes they'll be ionized. They'll be stripped of electrons. So there'll be charged particles flying through space. Or we can find them in molecular form, where they're making atomic bonds and making these bigger molecules. And we'll find dust, cosmic rays, all this stuff scattered throughout the interstellar medium, the space between stars. Right? Most of the stuff is going to be concentrated in nebulas. In fact, 99% of this stuff is going to be hydrogen or helium. Right? And the remainder, that last 1%, that's going to be that interstellar dust. Right? The dust is going to be the slightly thicker, slightly bigger materials. These are going to be rocks, silicates. And here's an example of a dust particle. And for scale, this is a micrometer, 10 to the minus 6 meters.